Hey everyone, today I'm going to go over titration, specifically base hydrolysis and also acid dissociation, because on the exam, you're going to get either this or this. So like you really need to know what the difference between both of these are, and like the similarities as well. There's more similarities than differences, but since in class we did mostly base hydrolysis, you might be following the steps associated with them one by one. But if you were given acid dissociation on the problem, you might get thrown off by some specific details, and that might cost you a lot of time. Ideally, this entire problem should take you about 8 minutes for each of these, so like eight. But you're only gonna be given two of these. Either it could be one, two, three, four, or like two, three. I don't know which one she's gonna give you, but that should take you 4 minutes. And the reason why I say 4 minutes is so you can spend another extra 2 minutes to go through any of the math that you did, just to make sure you have no mistakes and stuff like that. So that's why I'm doing this problem. So you guys don't have to stress about this, and you guys can go through this video, and I'm gonna post this empty sheet right here so you can kind of have a walkthrough of what's going on, and I'm gonna post the one that I finish up as well. But the whole reason I'm doing this again is so you guys don't worry about this question. Again, remember, this question is only gonna be 10 points in the exam. That has 9 more questions, and including an extra credit question that you probably should be worried about more than just this one question. So you shouldn't be spending way too much time on this question, is what I'm trying to say. So let's start with base hydrolysis, and then we'll go side by side, and I hope it works out because I am doing two different things side by side, and I'll explain the process after, like what we are actually doing after when I'm done with the problem, just so it kind of makes sense. So it's kind of the basic structure, right? You're gonna start with like some amount of volume of your weak base, right? NH3 is a weak base, right? And then if you look at the acid dissociation part, you're going to start with a weak acid. And all base hydrolysis is you're adding a strong acid to a weak base, and acid dissociation is you're adding a strong base to a weak acid. And once you get that made sense, when you look at the problem and when you read the problem, you have to understand which one you're dealing with. If you're dealing with a weak base, it's base hydrolysis. So you have to do the steps associated with them in the right order and properly. And if you're dealing with a weak acid like acetic acid, this is acetic acid, then you're dealing with an acid dissociation problem, right? So let's go through the steps one by one. And then I highlighted some red. The red highlighting is just the important stuff you need to get out of it, okay? So obviously I highlighted the Ka because you have to know the distinction between Ka and Kb and where you use both of them. And you'll see as I do the problem that it's going to be there. So if you look at this problem, number one asks you, what is the pH before adding HCl? What that means is basically you ignore everything after the first sentence, everything after the first part of the sentence, okay? And if you do that, you know that the only thing you really have in the solution is your NH3 in water, right? Because it's an aqueous solution. If you know that, you got to write your reaction down immediately. So when you write the reaction, you're gonna have NH3 aqueous added to water that's a liquid, right? And you can have an equilibrium arrows and a reaction that gives you NH4 plus and then OH minus, right? And then that's the same thing is true for the acid dissociation as well. You're gonna have your acid, which is your weak acid, right? Added to water, and you're gonna end up getting H3O plus and then your conjugate base, right? And then once you get that equation, everything becomes a lot easier because you know what to do afterwards. So if you didn't add any HCl, is your concentration that was given 0.5 millimeters of NH3 going to change? The answer is no. So if that's the case, then all you really have to do is just put that 0.75 molarity for NH3, right? Do we care about water in this case? No, because it's a liquid. So you can literally just cross out water. The only reason I put the water is to show you what's happening. So put the water down in the reaction, but cross it out because you know it doesn't influence your equilibrium constant K, right? And you'll see that later on, okay? So if this is, you're starting with 0.75 molarity of this, you're starting with 0 of this and 0 of this, right? Makes sense because this is when you add it to water, right? And the same is going to be true here. You're going to have 0.75 molarity 0 and 0, and again you ignore water. And I kind of kept the numbers right here. Like if you notice the numbers right, 75 and 0.75, like literally the same for both problems, just to make the math a little easier. So don't get thrown off if the numbers look a little similar from both sides. So I hope that doesn't happen. So in your change you can have minus x plus x, right? Plus x, because they're all 1-to-1 ratios. You'll not have. I don't think she's gonna ever give you like a plus 2. That's not gonna plus 2x. That's not gonna happen just because you're not gonna be dealing with like diprotic stuff. And don't worry about it. She's not going to give you that. It'll throw you guys off, and she doesn't want that to happen. So you go ahead and subtract both sides. I'm going to not put the m because you don't need that. X and x. And then do the same thing in both sides, right? Minus x plus x, and then you're gonna get x 0.75 minus x. Okay, now the next thing I do is I set up the equation, right? Because it's an equilibrium equation. You're trying to find the equilibrium constant, right? I mean, you're given the constant, but you're trying to find x, right? What you're trying to find here is x, so you can get the concentration of your OH and the concentration of your hydronium ion, right? Makes sense? So go ahead and write the equation down. It's going to be x squared. I'm going to move this up a little bit. X squared over 0.75 minus x, right? You get x squared because you multiply x and x, right? And then it's going to be the exact same here as well. So I'm going to do that right now. And you set it equal to your k value. But here's the question. The problem is this, what you're going to put right here going to be Ka or Kb? If you look at what you make in your products, you make OH, right? If you make OH minus, you have to use Kb, which means you have to convert your given Ka. That's why I highlighted Ka here, is because you have to convert it to Kb in order to get your hydronium ion concentration, right? But when you look at the other side, when you look at the acid dissociation, since you're making hydronium ions, you can just use your Ka. So let's just put the Ka value, which is given to be 5.8 times 10 to the negative 10 here. But here, you're going to have to do something. You have to convert your Ka to your Kb. So I'm going to divide the 10 to the negative 14 is Kw. You have to memorize this equation. It's she gave it to you in class, and memorize it so you know how to convert Kas to Kbs. Okay. Then you can go ahead and divide by the concentration Ka, which is 5.8 times 10 to the negative 10. So once you divide this, you're gonna get let's see, I got 1.7 times 10 to the negative 5. So this is your Kb. This right here is your Kb, right? So go ahead and do the math, and what you get for x is equal to let's see, 3.57 times 10 to the negative 3 molarity, and for x over here is going to equal to 3.67 times 10 to the negative 3 molarity. But I have a question for you guys. What is this x saying? What is this x? Like, what does it mean? If you notice what that x means, is if you plug it back right here, it tells you your equilibrium concentrations, right? And what x really is the concentration of OH minus and the concentration of your NH4, right? So if that's the case, all you really need to know for this one is that x also means OH minus concentration here, because you make OH minus. Here, it's going to be hydrogen plus concentration, or your proton concentration, right? And again, this is the same thing as saying this, so just so you guys don't get thrown off by anything, it's the same thing, literally the same thing. It doesn't really matter. I just use H plus for simplicity. So if that's the case, do you notice something that's a little bit similar? So that's a little bit different. This is where it slightly differs. Because you are given H plus concentration here, in order to find pH, which is what the question asks you to find, you can just use a regular pH equation, right? And you can plug in negative log of your hydronium ion concentration, which is 3.67 times 10 to the negative 3. And then you plug it in, I get a value of 2.43. And this is my pH for acid dissociation of the first one. But let's do the other one. If you were to do the same negative log of 3.57 times 10 to the negative 3, you get a value of, let's see what I get. I got 2.47. Now, question here. Is this the value of pH? Is this 2.47 the pH? No, it's the pOH, because you used OH concentration. You plugged OH concentration into the log equation. That's going to give you pOH, right? So this is the distinction that you have to realize. When you're doing an acid dissociation, this is what's happening. You're getting pOH, not pH. Oh, no, sorry. If you're doing base hydrolysis, you're going to be getting pOH, not pH. But the question asks you for the pH. So what you have to do is you take pH equals 14 minus whatever you got for pOH, which is the 2.47. So I'm going to do the math, and I think I got like 11.55. And again, I'm not really worried about sig figs right now. That's a you problem. I'm sorry, because I that's too much for me. I don't even remember how to do sig figs, to be honest. So that's the pH, right? So if you notice something, this is very basic pH, right? And this is very acidic. I want you to keep that in mind as we go through this problem, because there's a very important thing that's going to change as you go through these steps. And I'll show you in a graph illustration after we're done with the entire set, okay? So that's a pH. That's how you solve for the initial pH before adding any HCl or NaOH, depending on what you're doing, right? So now things get a little interesting. Now you start adding 15 ml of HCl for base hydrolysis, and you add 15 ml of NOH for acid dissociation, right? So if you go to the problem for the part B, I wrote the equation down for you, and you should write the equation as you go through as well, right? To make it easy for you, I wrote it. So basically, if you look what's happening here, you have your NH3 because yeah, you have an initial concentration of NH3 in the solution, right? But you start adding HCl. In fact, you added 15 milliliters of 0.5 molarity HCl, but HCl is a strong acid, so it dissociates completely when you add it to the solution, right? Which means your chlorine doesn't matter. Like the chlorine doesn't matter, it doesn't do anything. And same thing goes for the NaOH over here, right? It doesn't do anything. It doesn't matter for the Na. The only thing that matters is the OH minus because that's what interacts with your reactants, right? So that's the new, this is where you have to make your new equation, and you have your NH3, which you're starting with, plus your proton ions, which comes from your HCl concentration, right? And then you make NH4 plus, right? Aqueous, and they're all aqueous, right? And for the acid dissociation, you use your acetic acid, which is your acid, and your OH minus, which is your base, and you end up making the conjugate base, which is the CH3OO minus or acetate. And then you also make water. And again, in this case, you can ignore water because it's a liquid, right? It doesn't really matter. I just showed you because that's what you make. Some people get confused. They start wondering, where is the OH going? You make water because you take away this hydrogen and it leaves. This is a bit of organic chemistry. I don't want to get into it, but like just know that you make water and you ignore water, right? So let's get through it. Let's start solving for this now. So if this is the case, what is happening in part two? You're adding more volume. Your volume is changing. If your volume changes, by convention, you know molarity equals moles. Oops, I spelled moles wrong. Okay. Moles over volume, right? If your volume increases, so does your but your molarity would drop, right? Because it's an inverse relationship, right? Makes sense, right? So that's why you have to solve for moles for all of your parts. I still kept the ice table, even though you won't have access. You won't have access for this one because I'll tell you exactly why. So let's solve for the moles in this case. So I'm going to do it underneath here just to make a little bit easier. So I'm going to solve for the moles of you're solving for the moles of given. You're given moles of NH3, right? So that's basically, I'm going to convert the 75 milliliters to 0.57 liters, and I'm going to multiply by the molarity that I have given you guys, which is 0.75 molarity, and this is going to give me the moles of NH3, and what I got for that is 0.056 moles. I'm not going to write that down. Then you're going to get moles of your proton ions that you added. Again, you can ignore your chlorine. It doesn't really do anything. So I'm going to convert this to liters, and then again, the concentration that you're given is 0.5 molarity for your HCl, which equals what did I get? 0.0075. And this side, I'm going to do the exact same thing and find the moles of your CH3COH, which is acetic acid, which is going to equal to your concentration. Again, it's actually the same math. It ends up being the exact same thing because I use the same numbers. So that's why it makes my life easier. So I just use the same numbers. So I'm going to just literally just plug that same thing. Hope my handwriting is not too bad. So moles of your OH though, that's the only distinction here. You make OH, right? Because you used NaOH and therefore you added OH minus, right? That's a distinction that you have to make. And then you get your moles of both of these. And what you do with them is you plug it in your ice table, right? So go ahead and put 0.056 here, and then you're gonna put 0.0075 here and do the exact same thing both sides. 0.0, did I do some math issue? Let me just quickly double check. No, 5, 6, and then 0.0075. Okay. Now, what do you think is gonna happen here? And this is where people get something wrong because you don't know you automatically think that you have your NH4, but that's not necessarily the case. What's happening here is the hydrogen, being a very, very strong acid, is going to react with the NH3 and make NH4. Because hydrogen does not want to stay as hydrogen. It wants to react with something, and the one thing that's going to react with is the NH3, not the water. Don't get confused. The NH3 is not going to react with the water and make hydronium ions. It's just the H plus is going to react with NH3 and then make NH4. And the same thing happens here. Hydroxide is a very, very strong base. It does not want to stay like that. So it's going to attack the acetic acid and it deprotonates it. And again, I'm giving you the orgo explanation, but you don't need to know the orgo explanation, and you don't need to know that. Just know this is what's happening, and you form your conjugate base and your water, right? So if that's the case, what's happening here is what is your limiting reagent? That's what you have to know. And if you compare both of these numbers, you would know that your hydrogen ions are your limiting reagent, right? For both sides, right? If that's the case, you know you're going to consume all of it. The limiting reagent is consumed completely, right? So I'm going to subtract 0.0075 and then subtract 0.0075 both sides. And then if you subtract by this much, you know you're going to make that much of NH4, right? Because again, you're going to be adding by that much, right? Because think about it, this is just your regular stoic, right? Because if you consumed, if your limiting reagent was hydrogen ions, that amount of moles is what you make of your NH4, if that makes sense. And the same thing is true for the other side, right? If you had 0.075 moles and that's your limiting reagent, that's all you're gonna make for your conjugate base here, right? So I'm gonna go ahead and do that both sides, and I'm gonna get the difference for them. And I got, let's see, I got 0.0485, and this cancels out, right? Just making sure I put everything in so you guys can see what's happening. And then 0.0485, and then this is just going to be this, and then, and again, remember, this is all in moles, right? Just so you guys have a perspective. I'm gonna do a little bit something. I'm gonna move this slightly this way, and I'm gonna move this a little bit here so I can have room. Now, but the problem is, it's in moles. What do you think you're gonna do with the moles? You have to divide it by the total volume, right? Because think about it, you diluted the solution. The whole point of finding the moles of your product and your reactants is to know your new molarity. That's the whole point. So you need to know what the new volume is. And the way you get your new volume is, you started with 0.075 liters, right? The question said you started with 0.75 liters, and then you added 15 ml here. So you're going to add a point, what is it, 0.01 or something? So you're going to add 0.015, and that's going to give you 0.090 liters, right? And that means this is also the same, right? Because I use the same numbers. So I'm going to just go ahead and put that. So if that's the case, if this is your volume in liters, what do? You just literally just divide it by this, by the moles, right? Because again, this is moles over liters, and that gives you molarity, right? That's going to give you molarity, and I'll do the math for you guys just in a second once I start plugging this in. I hope my numbers are looking decent. Like, I know my handwriting is not the greatest, but whatever. So go ahead and divide that, and I got, for my equilibrium concentration, this is gonna be 5.38 times 10 to the negative 1 molarity, right? Because that's what you're trying to find. And I'm gonna make some room, so I'm gonna erase this. But you guys obviously I'm gonna erase this and just put that right there. Okay. And then this is gonna be 8.3 times 10 to the negative 2 molarity. And coincidentally, it's the same thing here because I use the same numbers. So just to make, again, my life a little bit easier. So go ahead and plug that in. So the reason why I'm doing it side by side is, again, to show you guys the distinctions and where you use POH or pH, and then what equations you use for the two problems. Even though they're doing the exact same thing, you're solving for the same pHs, the steps you get there, remember the reactions are slightly different. Like here, again, you use your hydrogen ions, but here you use OH, right? And that clearly dictates what products you get, right? And you really need to know this. So now that you got your concentration of your acid, so in this case, well, that's not an acid, that's a base. So let me actually give you some terminologies. I'm going to give you a terminology. What is this? This is the base. The NH3 is a base, right? So NH3 is a base. I'm going to put B, right? Probably the worst marker. Let's give you green. Okay, B, right? Which means this is your conjugate acid, right? HB, right? And then if I go with this side, this is your HA, right? For the acid, because this is an acid, right? HA means acid, right? And A minus means conjugate base. Now, the distinction you need to make is you can give B and A and HB and A, whatever works for you, works for you. But another way of thinking about it is you can think of B as A minus, and then you can think of HB as HA, okay? Just to make your life a little bit easier to see the differences. And you'll see why in 1 second, why that matters. So let's keep going. Now you have your concentration of both your acid and your conjugates, right? That's all that matters, and both your base and your acids as well. I hope that's clear. So what matters is that you found your concentrations. I'm going to highlight that right now. That's all that matters. This is not in liters. I don't know why I put liters here. Molarity. Okay, sweet. minus. Let me just make it a little bit clearer just so you guys don't get confused with my math. Okay, so let's move on. Now you're going to use your Henderson-Hasselbalch equation. And I'm going to do acid dissociation first because it's a little bit easier. Because all you have to do is just use pH equal your negative log of your pKa, your Ka, right? And your Ka is given as 1.8 times 10 to the -5 plus your log of your conjugate, what is it? Your concentration of your conjugate acid, which is conjugate base, my bad, which is going to be 3.8 times 10 to the -2 over your 5.38 times 10 to the -1, right? And this is going to give you a pH of 3.93. So I'm going to highlight this just so you guys see the answers there. So this is, again, an equation you have to memorize, right? Because remember, pH equals pKa plus log of your A minus over HA, right? Now that's the whole point why you should write down your HA and A minus, just so you can, when you're using the Henderson-Hasselbalch, you know what to plug in where. If you know your acetate is your A minus, and this is the concentration of your acetate, you plug that in. Oops, you plug that in right here, right? On the top, because it says it in the top, right? And you do the same thing for your acid, right? HA, right? So now let's go to the base hydrolysis, and there's actually two ways of doing this. And I'll show you the one that she did in class, which is just using the pH equation, which is a little bit easier in my opinion. Actually, I like the other way better, but like this way works. So again, you can plug in your negative log of your HA, and if you notice that you're given HA here, so you just plug in that given HA, which is 5.8 times 10 to the -8, no, -10, okay. -10 plus your log of, again, you need to know what your A minus is, but your A minus in this case is gonna be, what is it? It's gonna be this, right? This is your A minus, so this is your A minus concentration. You see how it's flipped in this case? And this is why I'm doing it side by side, so you guys know the distinction between what's happening where and why, right? So this is actually gonna go on top, and that's why I'm using the same numbers as well, so you can see like how the numbers differ from both of these, right? And then this is going to be 8.3 times 10 to the -2, right? And then that's right here as well, right? HB equals HA, right? That's why HA goes on the bottom. And what you end up getting is, what is it? What did I get? I got 10.05 for my pH, right? 10 for my 4.5 pH, okay? Does that make sense? So this is your pH. But there's actually another way of doing this. Remember how I gave you B and HB here? Like I gave you B and HB because it makes sense, right? NH3 is a base, so you put in B. And you know NH4 plus is a HB, right? Because it's a conjugate acid, right? You can actually use a different equation. I mean, it's the same, it's similar, it's still Henderson-Hasselbalch, but it's in terms of POH. POH equals PKB, right? Plus your log of your what is it? It's gonna be your what is it? Your HB at the bottom and then your B in the top. Do you see that? It still works out and gives you the same answer in the end of the day. Oops, wait, I think I flipped it, my bad. It should be this. It should be HB over B. And if you actually plug in the concentrations like that, you actually get the same answer. And where do you get KB? Someone might ask, oh, where's KB? Do I just have to solve it again? You actually don't have to solve for KB again, because remember, you solved it right here. You solved for KB right here. So you just need to plug this in here, and you can get POH. And then all you have to do is to find pH. You just take pH and subtract 14 by whatever you get, and for your POH, right? And then you get the answer. You in fact get the same answer. So what I'm trying to say here is do what works for you. If you want to just use the regular Henderson-Hasselbalch, remember that you have to flip the stuff that you're using right here. I hope that makes sense, okay? Because based off of your orientations, right? Like where's your acid and where's your base, right? You have to know that always, right? So whatever works for you, do that. If it doesn't work for you, then just stick to what works for you. So like if in class you did the pH version and it worked for you, by all means go ahead and still continue using this. But I like using the POH because it's a bit easier to see why for me personally. But that's how you do it. But end of the day, you get the same answer doing both methods. I'm not going to walk you through how you do with POH because it's not really worth the time. So let's go ahead and move on to the next part right now. So the third part, arguably probably the most difficult for most people, but let's go step by step and what's actually happening here. And you really need to understand what equivalence point really means. Like you need to know what equivalence point means. So equivalence point literally just means when you have equal amount of your weak acid or weak base to your strong acid or strong base moles. And you'll see that in a minute. And what I mean by this applies for both this and this, by the way, just so it makes sense. So what that means is, remember when you already solved for the moles of NH3, right? They go back here. This is how much you started with, right? You started with this much, so you already solved for it. So all you have to do is just plug that right back there. So if you plug that right here, 0.059. In order to be at equivalence point, you have to add the exact same amount in moles for your protons. That's literally what it means. And you're going to do the exact same thing here as well, right? Because this is what you started with, and that means you have to add the exact same amount of moles of OH minus, right? That's what this definition that I gave you guys really means. That's what equivalence point means. At what point in a titration is your moles of your acid, which is H plus, equals to your moles of your base for this instance, and at what point is your weak acid moles is equivalent to your strong base moles in your acid dissociation. I hope that makes sense. It's clear between both of them. That's why I gave you a dash just to see the differences between both of them, so you guys don't get confused, okay? So now, if that's clear, what do you think is going to happen now? What is your limiting reagent? Do you have a limiting reagent here? To be honest, no, because both are actually the limiting reagent. You have equal amounts, which means you're going to consume all of it, right? So that means it's going to change. It's always minus, right? So minus 0.59 minus 0.059. Then you're going to add plus 0.059. So you're going to end up with this, right? And do the exact same thing here, just so you guys can see what I'm doing. Plus 0.59. Let me just make sure it's 0.5. Oh, I kind of messed it up. It's not 5.9, it's 6. Oops, my bad. Sometimes I make some math mistakes. Don't be me in the exam. I could just copy it, and then this is 0, 0. Then you're going to get plus 0.056, and then I can just copy this. Okay, now if you notice what's happening here is that all you're left with is your your product concentration, right? The only thing you have left is your product moles, right? That's all you have left. You consumed all of your OH minus, you consumed all of your acid here, you consumed all of your base here, you consumed all of your acid here, right? Does that make sense? So if you consumed all and you're only left with the other product, what do you think is going to happen? You're going to flip the reaction. The only thing that's going to react is going to be, in this case, your NH4 and your water. And in this case, it's going to be your CH3COO minus with your water, right? Because that's the only thing left in the solution. So this is why you flip the equation. And a lot of people are really confused on why you flip the equation is because you run out of your initial reactant. You're done. If you only had 0.56 moles and you added that with 0.56 moles of your H plus, you use it all up. You're done. Your reserve is over, right? Which means you have none of that left, and the only thing you have left is your product, right? That's what it means. At equilibrium, the only thing that's left is your product. You have no reactants anymore. You're done with reactants. But now the products are going to react with the water. I know it's kind of hard to see, but your water is your solvent of this entire reaction. Before, it didn't play a big role because you had strong substances that react with what you have, and now it is going to play a role because you only have water and your product left, right? I hope that makes sense. But let's now start with our actual ice table for this problem, and this is where people were confused before, but now I hope that you guys have a better idea of what's going on here. So before I start with the ice table, you want to remember this is moles, right? This is moles, and then this is moles, right? You want to convert it again to your volume, right? To your molarity. Sorry, you need your molarity, so you need molarity of your CHCO minus, which equals this value, divide this entire thing by the total volume, because again, total volume in this case is going to be what? Your 0.075 plus, how much did you add? At equivalence point, oh, this is, oh, my bad. So this is where you, so again, so in order to get this part, the second component, this is going to be volume of your OH minus. And then for this part, your total volume is going to be your 0.075 plus your volume of your H plus. So, so in order to get that part is why you use the M1 V1 equals M2 V2. Because remember, if you're, let me actually write this down so it's a little bit more clear. So if moles of your NH3 equals the moles of your H plus, as shown right here, and that's what the definition of equivalence point means, right? This and this are equal, right? Let me just move this a little bit right here so it's not completely displaced off-centered. So if the moles of your base and your acid are equal, and in this case your acid and your base are equal, that means you can set this M1V1 equation, right? So now you know that moles N equals molarity multiplied, molarity multiplied by volume, right? So you're gonna get your M1V1 equals your M2V2, right? So what does that mean? So you can go ahead and plug in some values. So what is the molarity of your NH3? Well, it's given, right? It's given in the problem. In the very beginning of the problem, it says it's 0.75, right? So all you have to do is plug that in. And then you multiply by the in its initial volume, which is 0.075 liters, which you already did. So technically, you don't even have to do this math. It's just this number, right? It's this 0.056, right? So you can just plug that in. So what is it? Uh, oops. There you go. And then you can go ahead and you know the molarity of your your HCl was what, 0.5. So plug that in, and then you have your V2, right? So now all you have to do is just divide this by 0.5 both sides, and your volume 2, or your volume of your H plus, is gonna be what is it? What did I get? I got point. Give me 1 second. Sorry, guys. Yeah, I got 0.112 liters, and because the same math applies for this because I use the same numbers, so the volume 2 or the volume of OH is going to be equal to 0.112. So I can go ahead and substitute that number here. So go ahead and substitute this number here, and your total volume ends up being 0.187 liters, and plug that in back here, plug this number in here as well. Your total volume ends up being the same, right? Because I use the same numbers in this case, so it ends up being the same for this as well. So if this is your total volume, and then so if this is the remainder moles you have, and this is your total volume, what are you going to do? You're going to divide that number by this to get your molarity, right? So that's how you get the new molarity, and then you can so all I have to do here is go ahead and take let me actually give myself a bit more room. So all you have to do is go ahead and molarity of your, what is it? NH4, yeah. NH4 plus is going to be equal to 0.056 divided by 0.187, right? This is moles. And again, this is liters. So this is going to give you, I got, what did I get? 0.3. I got something 0.03 molarity, right? And when I do the math here as well, when I substitute, basically move this right here and then divide that, and I get the same number because I use the same numbers again. So, oops, not liters, it should be molarity. Okay, perfect. Now you can go ahead and start plugging stuff in your ice table, right? So you know your initial for this is 0.3 because you just solved for that, right? And then the same thing, initial is going to be 0.3, right? Ignore water because water is a liquid, so it doesn't matter. Again, but this is going to be 0 because you didn't make anything before. I initially had 0, but you're going to start adding x, 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 and then x. And this is me subtracting x because you're losing some moles, right? Molarity, right? And then you're going to be ending up with 0.30 minus x plus x, and then plus x, right? And then 0.3 minus x, and then x and x. Oops, no, plus x. Okay, so if this is what you have in equilibrium, what do you think you're gonna do? Again, you're gonna set up your Ka, right? You're gonna set up your equilibrium constant, right? So you're gonna have x squared over 0.3 minus x. You're gonna have x squared over 0.3 minus x equals. Now, here's the deal. So here's the deal. What do you use again? I'm gonna ask you again. What are you gonna use? Are you gonna use Ka or Kb? Again, look at the product you're making. The product you're making is H3O, which means it's an acid. So you're going to use Ka, right? Ka, A for acid, right? So you can use acid Ka. And that's given in your problem, right? You're given in the problem. So you can go ahead and just plug that in. And so when you plug Ka in, just 5.8 times 10 to the negative 10. And I go ahead and solve for x. And when you solve for x, it's also going to be equal to your proton concentration, right? Because again, this, right, same thing. So which equals, I got 1.32 times 10 to the negative 5 molarity. And let's go ahead. What about this one right here? But acid, what about this part? Look what you're making. You're making OH minus, so you're going to use Kb, right? So does that mean you have to solve for Kb? Yeah, because you didn't solve for it. You're given Ka here, right? You're giving Ka here. You're not giving Kb, so you have to solve for it again. So how do you solve for it? Again, you know that 10 to the negative 14 divided by your Ka, which is given in this case. So go ahead and 1.8 times 10 to the negative 5 is going to give you your Kb, and then that Kb is going to be 5.6 times 10 to the negative 10. Oh, okay, this is really bad. Okay, this is really bad. Give me 1 second. It's going to be your Kb, and your Kb is going to be equal to 5.55 times 10 to the negative 10. So all you have to do is just plug that in here, right here. 5.5 times 10 to the negative 10. And then you can solve for x. When you solve for x, you're going to get your OH concentration, right? And then, so which means your OH concentration is going to be, what is it going to be? Let's see. I get OH concentration here, I got to be 1.29 times 10 to the negative 5 molarity, right? Now, how do you solve for pH? Let me move stuff a little bit down just to get a bit more room. This is a bit easier to solve for pH. If you think about it, it's actually really easier. All you have to do is, what do you have left right now? The only thing you have left is um, your proton. You only have your protons, right? You made protons here, and then you made OH. So you made protons here, and you made your OH here. So all you have to do is pH. In this case, since you made acid, you can just plug in that number, the negative log of 1.32 times 10 to the negative 5, and then that's going to give you a pH of 4.88. Okay, that's your answer. So, and then here you're gonna get POH, right? Because what you got was your OH concentration, so negative log of 1.29 times 10 to the negative 5. And once you plug that in, you get a POH of 4.89. But you gotta get your pH because that's what the question asks for. So you take 14 minus 4.89, which is gonna give you 9.11. So that's your pH, and that's it. That's how you solve for this equivalence point question. It seems very hard, and just if you do the first initial reaction and you see how it's getting consumed, everything is getting consumed right here, and you make all your products, and because you only have your products, it's going to react with your water to form this stuff, right? And then you can see how you set up a new ice table, and the new ice table is going to tell you the right answer or the right pH, right? Because you end up making either acid in base hydrolysis at equilibrium, or you're going to make base or in your acid hydrolysis, right? So this is why you need to know the differences between them, because it can get confusing. You don't. Some people just do the base hydrolysis, and when they get to acid dissociation problem, they're wondering why is it not H plus. This is why. Okay, so you should know the distinction between them. It helps a lot, and doing these two problems side by side is honestly the best way to go about it. So last but not least, the fourth and final part. All right, the fourth and final part. If I were to actually go back up here, this is literally always going to be when you have excess HCl, and when you're gonna have XS, can I not spell? Okay, XS NaOH, right? So what that really means is, if you notice in what is it, step 2, your limiting reagent was your H plus, right? Your limiting reagent was your H plus, and your limiting reagent for the acid dissociation was your O minus, right? But now your limiting reagent is actually going to be flipped. That's literally all it's really saying. And that's going to change. It's going to make your life easier, to be honest. And let's go ahead. How much moles do you still have of your NH3? Not still, actually. How much moles of NH3 did you begin with, right? You began with this, right? You always start with the same amount you started with. So that never changes. These problems, these steps never interfere with each other. So you don't plug in a value that you got from the previous steps into this problem. That's not how it works. You plug in what you're initially given based off of the problem. Treat each individual steps as their own individual problem, and your life will get a lot easier. Okay? So plug that in, and now you need to calculate how much moles of your protons, and how much moles of your OH you have. I'm gonna do this right here, just to make a little bit easier. So the moles of your H plus is going to be equivalent to, let's see, how did I do this? Where did I write it? Yeah, so most it's going to be 0.125 liters, because you inputted what the question says. You inputted 125 ml, right? Like 125 ml, right? Just so you guys see that. So it's going to be 0.125 liters, because it's always liters, multiplied by the molarity, which is 0.5, and it's going to give you some number. And then this side, the moles of your OH minus is going to be equivalent to 0.125 liters multiplied by 0.50 molarity, right? It's going to give you a value of 0.0625 moles, and then 0.0625 moles. Now, a lot of people get confused. Where are you getting these numbers? And again, you have to go back to the question, just like I said before, just so you guys reinforce like where to go back. When you're confused of where did you get that number, it's always coming from the question itself, right? The 0.5 that you see here, this point, the 0.5 molarity, you see here, really comes from the question itself, right? Go back to the question. It says you're titrating with a 0.5 molarity HCl. You're titrating with a 0.5 molarity NaOH. That's where the molarity comes from, okay? So the whole reason you're multiplying is to get moles, and then once you get moles, you can go ahead and do exactly what you did before. Plug this number right here. But like I said, this is going to be your limiting reagent here, and then this is going to be your limiting reagent here, right? Your LR, right? So if you do the math, you subtract both sides, right? Because your limiting reagent is consumed, right, all throughout. This is like Gen Chem 1, right? And then plus your 0.56, and then you're going to only have, oh wait, oops, my bad. So you're gonna have 0.056, and you're gonna have something left over here. What is that number? What did I get? I got 0.0065 moles of H left, and then do the exact same thing here. I hope like me doing this side by side is not confusing you guys more. If it's confusing you guys more, I'm sorry. It's not my goal. So it's just to show you the differences, and then you're gonna get 0.0065 moles here. Okay, 0.056 moles. I have a big question for you guys now. So if you notice this, at equilibrium you have some concentration of your H plus, right? Oops, some concentration H plus and some concentration NH4, and in this case you have some concentration OH minus, like moles of that, and then some moles of your there you go, some moles of your water, right? And not water, I mean your CH3COH, right? And again, you can ignore water here because it doesn't do it. It's liquid, so it doesn't matter, right? So if that's the case, what matters more? What matters here between these, right? That's what you have to understand. And the answer to this is the only thing that matters is what's strong. Literally, that's all that matters. Your H plus. That's why I highlighted it in red. The only thing that matters here is the remainder of your protons, the remainder of your OH, right? This right here, this is all that matters. Because you ran out of you're done with your reactant, right? You're done with this, right? They're all done. The reactance is over. There's no buffer anymore. You're done with buffers, right? Step 4 that has no buffer in it. In order to have a buffer, you have to have both of your conjugates, right? You have to have both your conjugates. You need to have this, some amount of this and some amount of this to be considered a buffer. If you ran out of all this, this is not a buffer anymore. So if you only have, so the only thing that's going to influence pH in this case is going to be your proton concentration or your hydroxide concentration, depending on the question that you're dealing with, right? So how do you do this? So all you have to do is literally divide this by the total volume. And again, how do you get the total volume? Well, you add up total volume is going to be that 0.125 plus that 0.075, right? And then here as well is going to be 0.125 plus 0.075, and you get 0.2 liters, 0.2 liters, right? Once you get 0.2 liters, just literally just put that right back here, liters. And it doesn't matter, again, as I said, this doesn't matter. This doesn't matter because it's not a buffer anymore. If it's not a buffer, it's not going to influence pH anymore, right? So go ahead, and what you get for the concentration, this is going to give you a concentration of your protons, and then this is going to give you your concentration of your OH minus, which is hydroxide. And I'm going to move this out of the way so I get more room. And let's see what I got. I got 0.0325 for my molarity for my hydroxide, my proton concentration, and my OH concentration is 0.0325 molarity. Okay, so now again, if you have your protons, just use the regular pH equation, right? pH equals negative log of what you got for your proton concentration, and that's gonna give you 1.48, and that's your answer for this part. And then here it's going to be POH because you solve for the concentration at OH minus, right? So negative log of 0.0358, oops, 3, you're going to get, I got 1.48. And then what you're going to do here is, obviously, pH is 14 minus the number, and you're going to get 12.51. And I might have done some math issues throughout this, and I'm sorry if I did that. But if you recognize that I did math issue, that means you're on the right track. So it's good job. So that's it, guys. It's literally it. That's how you do an acid-base equilibrium problem like this, and so that's how you really do acid-base equilibrium problem like this for titration. And the whole reason why I wanted to show you this side by side is to show you the differences, and I want to show you some patterns. So I want to show you how you can check your work. If you stayed up until now, thank you for taking your time to go through this, and I want to show you some patterns and see whether you're doing it right or wrong. So for base hydrolysis, look at the pH you're starting with. You're starting with a high pH, right? Like this is your pH before you add anything, right? Before you start titrating it with HCl, right? It's 11.55. That's very basic, right? But look what happens to your pH. It goes from 11.55 to 10.10, right? And then it goes from 10 to 4.88. And then it goes from 4.88, it's going to go to your 1.48. You see that? It lowers. Your pH drops. Why? Why? When pH lowers, that means you're becoming more acidic. But why though? It's because you're adding HCl, right? It becomes more acidic. And I'll show you a diagram that illustrates this further up, but I'm going to show you the trends for acid dissociation. You start with see how you start with a very acidic solution? Like before you add any NaOH, you're starting at 2.43. That's very acidic, right? And then, but here at step 2, it's getting a little bit more, the pH increases slightly, right? And then it goes to 9.11. That's very basic, right? And then it's at 12.51. That's very basic. So what I'm trying to say is, if she gives you a problem, like for example, like she gives you 3 and then 4 to solve, ask you to solve it, and you get like a higher number here than here for acid dissociation, you did something wrong, right? And then if she gave you a base hydrolysis problem and she asked you to find, she asked you to solve 3 and 4, if you get a lower number here than compared to here, you did something wrong. So it's a way to go back, and if you notice the trends, it's a little bit easier to tell if you're doing something wrong or you made a math issue, right? Math error, right? So that's kind of a good, nice way to like know if you kind of like messed up, right, in the question. So now I'm gonna go, in order to solidify this better, I'm gonna draw out the what is it? I'm going to draw out the curves, and I think it's going to help you a little bit better to see what actually is happening when you're doing titration. So this is going to be pH. Your y-axis is pH, and obviously the max pH you can have is 4, and the lowest pH is going to be 0, right? So I'm going to go ahead and keep the stuff that you need to know. So in this case, when you're doing base hydrolysis, what is your titrant? You're titrating the solution with HCl, right? So that means you're adding protons, right? You're adding protons. So I'm gonna put H plus, concentration increasing, right? And the x-axis is gonna increase over time, right? Here it's gonna be OH minus because it's base hydrolysis, right? I mean it's acid dissociation, right? It's acid dissociation. You're adding OH. So if you're adding OH, your OH concentration is increasing over time, right? So let's draw this out. Again, if you had the initial pH was like what, like super low, like 11, super high, right? For this one, 11-ish. So that's what makes sense, right? You're dealing with something, you're dealing with a weak acid. This is weak acid. Weak base, sorry, my bad. Sorry. Weak base. This is weak acid. Just so you know what you're dealing with, right? And thus this is gonna be your base hydrolysis, and then this is gonna be your acid dissociation, right? So if that's the case, it's starting at a very high pH. And it's going to go down, 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 down. It's going to look something like this. And at this point is your equilibrium concentration. That's all you have to know. So initially, you start with a high pH, but as you add more, as you start adding more hydrogens, start adding more of these, more concentration of hydrogen, more moles of that, your pH starts to drop, 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 and plateaus out, right? It makes sense, right? Think about it. Just look at the trends you made. You went from a pH of 11.55 to a pH of 1.48. And doesn't this graph look pretty much just like that? Like assume this was 11.5, and this right here was a 1.48. And the equivalence point, which is right here, your pH is gonna be what did you get? A 4.88. 4.88. My scale might be a little off. I'm not trying to get for perfection, but you guys get the idea, right? And then the opposite is going to be true for this, right? Because I told you guys that your pH starts very low here, but then very low for acid dissociation, and then it increases to like a very high number. So let's draw that out. So it's going to look something like this. Then your equivalence point is still going to be here, right? And then let me just draw some stuff out, right? As you start adding OHs, your pH is going to go up, right? So you can assume like right here is going to be like that 12.57. You can assume right here, I mean, I'm not, and the equivalence point is going to be like 9.11. I probably should have like pulled it up a little bit, but whatever. And then you started initially with 2.4. Right, so this is going to be like your 2.43, right? So why am I showing this? The whole point of me showing you this is to know what's happening. Because even though they're both titration, you're adding a titrant to the solution. You're either adding a strong acid, to a weak base, or you're adding a strong base to a weak acid. That's all acid dissociation is, and that's all base hydrolysis is. The same steps, but you do more work some parts, but then you do less work on the other steps, right? If you notice these trends, and if you go through this thoroughly, like it's gonna help you guys out, and I believe so. And I would suggest you guys to not spend more than like 1 or 2 hours for this question to practice. Like after this video, if you guys watch it, don't spend more than like 2 hours. Watch this video, go through them multiple times, rewrite the questions, use the empty slot that I gave you guys to practice on. And then make your own problems. Like the one thing I would suggest is, you know, the numbers I gave you, like these numbers can be interchangeable. That's what Maddie really does. Dr. Maddie really only changes the volumes of the initial stuff, and she doesn't really change anything else, right? If you change the volumes and you start doing them, that's like good practice. You just made a new question by yourself, right? And if you're always, so one pro tip that I'll give you guys, if you're confused with what acetic acid is and like what acetate is, I'll literally just rename this as HA, and then I'll rename this as A minus. Like A minus, and then this would be H, just to make your life easier. And this could be named as base, and this could be named as HB, or this could be named as A minus, and this could be named as HA. Although the A minus and the HA for a base hydrolysis is not the convention, it doesn't really matter. As long as you get the right answer, that's all that matters. So go through this, and I hope this worked out for you guys and helped you guys out. I'm sorry if the video was too long. 2x this if you needed to, or like 1/2 the speed, just so you guys get the information. I hope I didn't mess up the math or anything. I didn't do sig figs because I don't care about sig figs, but Dr. Maddie does care about sig figs. So please note your sig figs and just look at the sig figs at the very end. Once you get the hang of these problems, start working on sig figs so you don't lose like some points on those, right? So again, I want you guys to be able to. I want you guys able to do each of these in 8 minutes, and then what that basically means is 2 minutes for each part. Practice, 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 and you guys should be ready for this in no time. And last but not least, if you're not really getting this problem, it's fine. Move on. This problem is literally only 10 points in your entire exam. Worry about the other problems that you could get right, right? This is not, in my opinion, this is really the hardest problem because there's so many steps associated with it. You think that all of these stuff are interrelated, although they are in titration, calculating each of these really they're not really interrelated. The only thing that I would say would be interrelated is at step 4 you need to know the how much volume you defer by. That's about it, and that's using the cheating method, which I didn't go over. Don't even worry about it, actually. Never mind, don't even worry about that. But that's basically it. I hope that made sense. I hope you guys ace this question, by the way, if you guys get it. She could give you obviously either one of these. That's why I gave you a presentation showing both of them side by side. So good luck, and then bye.